First of all, I'd like to thank the organizers, especially Antoine, George, for inviting me to this very interesting discussion meeting. And I'm particularly honored to give the first talk of this meeting. I was noticed the last evening by Professor Krishnamurti that I was the first speaker, but anyway, I think I could prepare. And I'm very happy to be back in Bangalore. During the last visit was October 2012, where I had a chance to visit the famous Durga Puja in downtown Bangalore, and we could explore, could see very beautiful things like this. So it's really my pleasure to be back here. And these are my collaborators of this work. These are people from my group and Professor Oshima in Tokyo University doing photon emission experiments. And high quality thin films samples, strontium vanadates film has been provided by Professor Kumigashira's group in KK, and some hard X-ray photon emission at Springate, and strontium molybdate. I had a very nice collaboration with suggestion by Antoine. And let me start with the standard Mott Hubbard picture from in which you can control the electron correlation and the metal insulator behavior as a function of band filling and correlation strength, which is denoted by U over bandwidth or charge transfer gap over bandwidth. And above a critical point for integer band filling, in this case 1, the system goes to Mott insulator, and otherwise systems are so-called correlated metal. And there is some insulating region maybe due to disorder or charge ordering around the Mott insulator line. And so let me first review our earlier work on the on this line, namely strontium vanadate and calcium vanadate is a prototypical transition metal oxide with band filling of 1. If you distort, this is an almost cubic perovskite. If you distorted the crystal like this, then the bandwidth is narrowed and the U over W gets bigger, but still below the critical point of Mott transition. So these two are metal, good metal, and without magnetism, magnetic ordering or any superconductivity. So this is a typical frame liquid C over gamma, C over T or gamma is finite, and resistivity follows T-square behavior. And so we expect to see something like this in by photon emission due to correlation. We expect to see a quasi-particle peak with reduced spectral weight and incoherent part above and below the quasi-particle band. And this is exactly what you have been why this school and workshop are going on. So-called dynamical mean field theory can predict this behavior as a function of U over W. And strontium vanadate and calcium vanadate are probably located from below the critical Mott transition, but somewhere around here and here. So the spectral effective mass correlation should get stronger, and spectral weight of the quasi-particle peak should be smaller in calcium vanadate compared to strontium vanadate. And this is our very, very early work. And probably we believe we did observe such a behavior of spectral weight transfer. But later it turned out that this is surface contribution was significant. So later, more bulk-sensitive photoemission spectroscopy like this, or careful decomposition of the bulk and surface signals has to be done. And, but in the bulk spectra, still we see coherent and incoherent part, and this width of the coherent part is reduced by a factor of 2 compared to LDA bandwidth. So our ratio is something like this. And indeed, the electronic specific heat enhancement is also consistent with band narrowing, factor of 2 enhancement. And there has been a little bit controversy whether strontium vanadate and calcium vanadate are different or nearly identical. These people claim these are identical, but DD's group find clear difference. And okay, then we should go to band RPES to follow the band dispersion. And for this D1 system, the Fermi surfaces consist of 3 penetrating cylinders because the 3 T2G band forms nearly 2-dimensional band dispersion. So the 3 cylinders are orthogonal to each other, resulting in these 3 Fermi surfaces. And by growing single crystals, we could observe such a penetrating cylinders. This is a Fermi surface, and cut on this pink plane gives you this, and the perpendicular cut gives you this intensity distribution. And calcium vanadate is a little bit broader, probably because of the distortion. The band splits compared to strontium vanadate, cubic strontium vanadate. And if you look at the band dispersion, actually calcium vanadate is coherent part band dispersion of dx, y, yz, yz and zx. Dispersion is less for calcium vanadate compared to strontium vanadate, and Fermi velocity is 20% different between strontium and calcium. So this is our background, and so today's outline is first I show you some overall behavior of strontium vanadate, and then look at the low energy and high energy part, and then I go to Hund's metal strontium molybdenum O3. So to discuss the self-energy more quantitatively, we need high-quality samples, which could be provided by epitaxially grown thin films on strontium STO substrate. Because of the epitaxial growth, the crystal is a little bit distorted, but due to strain, but distortion is very small, so we can neglect the distortion. So the RPS spectra becomes much better compared to the cleaved single crystals. And this is pink cut. You see clear DXY band and YZ and ZX band. This is side view also. And coherent part and incoherent part like this. And this is a wide range spectra, including oxygen 2p band and vanadium 3D. And of course, we are interested in this vanadium 3D part, shows clear dispersion. And incoherent part, not very much. But still, there is some very weak dispersion, and intensity modulation exists. Maybe you can see this view graph. The coherent part is, this of course exists, but its dispersion width is about half of the LDA prediction. And incoherent part, spectral weight is mainly concentrated within the Fermi surface. And this is a DMFT simulation by Marcelo Rosenberg. And actually, incoherent part also disperses, and spectral weight is confined within the Fermi surface. Of course, not as so strong clearly as coherent part, but vaguely confined within the Fermi surface. And this is also early DMFT LDA calculation by Nekrasov et al., Ole Andersen's group, basically reproduce these features. And but these features can be reproduced in a very simple model, namely just free electron dispersion plus this analytical form. I think this is the simplest analytical form that you can imagine for that capture the frame liquid properties and global high energy properties. And actually this incoherent part is weakly dispersing, and spectral weight is confined with this. Okay, so very first, low energy part near the frame level. The self-energy can be conventionally deduced by measuring the band dispersion and the width, peak width, to deduce real part and imaginary part of the self-energy. And first, real part is reflected by so-called not only band narrowing, but also fine structures called kink in the band dispersion, which was first discovered for high TC cuprates already 10 years ago. And there has been a lot of discussion whether this is due to magnetic excitations or electron-phonon coupling, but this is kink. It's very ubiquitous. Yeah. So this existence of kink means that self-energy has a structure near the frame level. And you can see for strontium vanadate, we could see also this not so pronounced, but slight change in the slope, which is reflected by this, some change in the slope at 60 or 70 millieV, which is identical to cuprates. And correspondingly, the width shows a slight increase because kink and step are mutually related through Kramers-Kornick analysis. And so the same as cuprates. And there is also a so-called high energy kink. If you trace this MDC peak, peak in the momentum distribution curves, the dispersion then gets, slope gets bigger below about 300 millieV. But this is very tricky. People do this analysis very often, but by looking at the MDC peak dispersion. But if you look at the EDC peak, then this goes in the opposite direction because this there is some band bottom around here, and so this is this purple line is EDC peak and MDC peak, and the big structure due to high energy kink, so-called waterfall. But if you follow the EDC, the kink is still there, high energy kink is still there, but becomes much weaker. So, but anyway, this is was first observed for cuprates, but seem to exist in the other system, like strontium vanadate. So we believe that this is generic properties of correlated, the self-energy of correlated systems. And then we go back to a high energy part, include high energy part. So let me explain how to deduce the self-energy over a wide energy range. Wide means a few electron volts from the frame level. This is experimental data from k equals 0 to frame level. Band disperses, and incoherent part does not disperse so strongly. And then, and of course, this is nothing but the imaginary part of the Green's function. But we need empty part also. So we have to do some assumption. But we are missing. Empty states information is experimentally missing. So we just symmetrize at momentum kf, but just ignore these empty states. But anyway, then we make Kramers-Kornick transformation to obtain real part of the self-energy to get the complex, real part of the Green's function, and to get the complex Green's function. Then put this Green's function into a Dyson equation to deduce the self-energy. So basically, this can gives you this kind of real part and imaginary part of the self-energy. But because of this assumption, insufficient experimental data, And we made the assumption that this is symmetric and anti-symmetric with respect to the chemical potential. But this is not too bad, but not very good. So I will come back to this assumption. And then, if you like, you can integrate over momentum and obtain the local self-energy and put it into the this equation, and to see whether this agree with the initial input. And if this agreement is good, then we stop and we can say that we have obtained the self-energy experimentally by iteration. But if not, we come back to this and go this iteration several times. And this is a final self-energy. But under the assumption, this is local self-energy, under the assumption of electron hole symmetry or asymmetry. And I mentioned a very simple analytical form of the self-energy. This capture most of the features in this experimentally observed self-energy. But of course, the electron flow are not symmetric. So this is a DMFT calculation by Nekrasov et al. This peak is bigger in the empty state, and dispersion is a little bit different. Also shown by Ferdi-Arias tier 1, and especially Zilke-Biermann pointed out that the maybe assumption, the assignment of the empty states, this is experimental data of old inverse photoemission data. Probably according to Zilke's calculation, empty states assignment is quite different from occupied state. So we have to study a lot more about these empty states also. So in the final 5 minutes, let me talk about the Hund effect in glutamate in the system. So I have talked about the D1 system, which is strontium vanadate and calcium vanadate, but D level is degenerate, and especially the early transition metal oxides, T2G level is triply degenerate, and so 6-4 degenerate, including spin degeneracy. So we have to take into account, as pointed out by Antoine Georges and his collaborators, and especially for half filling, the effective U, including Hund's coupling, becomes much bigger than the other one. So the half filling, the Mott initiating line is much more extended than this simple picture. But for other configurations, the effective U is U prime minus J. U prime is a Coulomb interaction between different orbitals. And so the correlation gets weaker. So this Mott initiating line is reduced, shrinks, and critical point is much below and much above the original U over W equal 1. And, but more interesting point is that the this region, although this is metallic and should be weakly correlated, but actually the renormalization factor Z is very small. In this white region is small Z region, which means quasi-particle near the film levels are strongly correlated. So, and because of the Hund's J, so this is a new phenomena, and maybe can be seen in another figure in Antoine's paper. Okay, so for D1 with increasing J, Z gets bigger, which means correlation becomes weaker. And for half filling, if increase J, the U effective increases. So correlation increases and the Z gets smaller and critical point becomes shifted in opposite direction. But in between D2 and D4, this region, this low or small U part and large U part shows opposite behavior. Actually, combination of this for this part and this part mimics this. So, probably this region is quite special and maybe called Hund's metal. Actually, our old data on strontium vanadate does not fit this typical behavior of strontium vanadate, in which the band narrowing and specific enhancement is almost identical. But here, the specific heat is enhanced by a factor of 4, very strongly correlated, but bandwidth does not change very much. Because probably this enhancement is, so U is small in 4D system, so the bandwidth is not much enhanced, but because of J, the low energy quasi-particle becomes heavy. And strontium vanadate has, so this is ferromagnetic, so a little bit complicated. So we look at the Pauli paramagnetic metal of strontium vanadate, which has D2 configuration, which shows a nice ferromagnetic behavior, is mass enhancement. And well, these are data. The molybdenum O4D band looks like this. Experimental data, LDA and DMFT, LDA plus DMFT with orbital generosity incorporated. And, but unfortunately, the initial data does not agree with the theory because of this hump. I will not go in too much in detail, but let me just mention that this may be due to so-called plasmon satellite, which has been known for many decades for photo emission spectra of simple metal. For example, magnesium shows second peak separated by plasma energy. And in this strontium molybdate, plasmon is 2 eV, and actually core level shows, all core level shows plasmon peak. So we consider that this is due to plasmon, and then the remaining part agree pretty well with the experiment, and width does not change so much with between LDA and the experiment and LDA DMFT, but experimental specific heat is enhanced, which is different, again, different from D1 system. So maybe we plot this strontium vanadate and calcium vanadate, and strontium, sorry, this is MO, molybdenite, and ruthenate. So this is a conclusion. So we have shown that 70 millieV kink is maybe, I didn't claim so strongly, but it is so ubiquitous that we consider this is due to electron-phonon coupling. And high energy kink is a generic feature of electron correlation, and the self-energy could be reduced for entire spectral range, but empty states has still some problem. And I just mentioned that these compounds are so-called Hund's metal, and obviously we need angle-resolved photoemission data for this Hund's metal. Thank you for your attention.
Are there questions or comments? We have few minutes. Yeah, please.
So the bandwidth, I'm guessing you are getting by looking at the full R-based data. The bandwidth you are getting by looking at the full R-based data and up to the point at which you get a signal. Is that correct? When you are looking at the bandwidth renormalization?
Yeah, if we have RPS data, yeah.
Yeah. But the specific heat is supposed to be dominated by the mass around the Fermi surface.
Yeah.
Complicated material, why would they just be proportional?
This is exactly what why I mentioned this is needed, because we guess that band dispersion shows a kink near the frame level, and at low energy side, the dispersion is very low, and then, yeah.
Could you go back to your strontium molybdate, please?
Yeah.
If you have a plasmon at 2 eV, which is so strong, shouldn't you see something at 4 eV then also? How far did you measure?
Well, yeah, I
It would be interesting to search for replica then, because
Yeah,
it's so strong.
I don't know, this is a,
Okay.
but in valence band, let's see. Yeah, if second replica exists, this is
Okay.
already in this region, so it's difficult.
Sorry, I had a very naive question. Your experimental self-energy is much broader than the model calculation self-energy. But is that all right? I mean,
Yeah, for example, yeah, much broader. Yeah, of course, resolution limited, but yeah, and actually near the frame level, this is a conventional method, and this is iteration method, and the agreement. Actually, not so different. Of course, we miss this fine structure, but fine structure, theoretical point of view, this fine structure is also depends on theory. So I think agreement is pretty good. Yeah, electron hole asymmetry is a problem, but otherwise, I think.
Yeah, of course, there is no direct determination of the experimental self-energy. So what Tsushi and co-workers did is to assume a particle hole symmetric self-energy and then do some iterative procedure, which is described here to get reasonable agreement with the data, although the AMPES data, of course, provide information only on states below Fermi surface, right? So we know from all the DMFT calculations that, in fact, there is very strong particle hole asymmetry. And this is playing a big role, in fact. I think we'll hear talks about that. So I think this is one of the reasons why in other words, I think one thing which is emerging is the need to have spectroscopies on the dark side, on the empty states, that would provide extremely interesting information on these correlated systems. And I think this is probably what's going on here.
Thank you.
Are there further questions or comments?
can you use your DMFT calculations and then from that you have the asymmetric self-energy? But suppose you take the negative part and symmetrize, would you get something?
So let's thank the speaker once again.
Thank you.